This chapter deals about current and resistance. I will start with the definition of the current. We can define simply the current as the direction, the motion of charges in a certain direction. For example, if the current is from left to right, that means that the positive charges are moving from left to right. And this is just the convention. But if the current carrying charges are negative, then the current and the direction of the motion of the negative charges are always opposite to each other. So if, for example, the negative charges are moving from right to left, then the current, we say, is from left to right. Okay, so this is just the convention. And the next question is, what is the source of current, or what are the current carrying matter? All we know that the electrical conductors, like metals, like salty water, conduct electricity. That's because in the medium of the material there are current carrying charges, particles. For example, inside metals there are free electrons. That's why all the metals are conductors. They conduct electricity, and the motion of these charges, for example electrons in metals, at, let's say, room temperature, it's very random. In fact, a free electron inside a metal goes in a certain direction, whatever the direction is, but it cannot continue its motion without stopping, because there are many different electrons, other electrons around, and it will collide. When it collides, of course, it will change its direction of the motion, and it will collide again. So normally, if there is no any electric field or no any potential difference between the endpoints of any conductor, the free electron moves like this. But they move very fast. Okay, but on average, they have certain speed. And for example, for a copper at room temperature, 300 Kelvin, the average speed of free electrons are like 10 to the 6 meter per second, 1 million per meter per second. This is a very fast speed. And because of this fast speed, the time between each collision with other electrons is very short, and we call this time as tau. And for copper at room temperature, it is around 3 times 10 to the minus 14 seconds. So it is very short time. They collide with other electrons or atoms. Well, the next question is, how many free electrons inside, let's say, 1 meter cube of a copper? For copper, this number is called as the number of electrons per unit volume, and this we denote as small n. So this is the number of electrons per meter cube, and for copper this is 10 to the 29. It's again a huge number. It's comparable to the number of atoms per meter cube. Well, you can say that because this motion is random, and each electron has an average velocity vector of 0. Well, the speed and the velocity are different things, of course. One object may have a very high speed, but it may not changes its location from one point to another point. In that case, its average velocity will be equal to 0, or its average relocation or position difference will be 0, because it will go inside by very randomly, and so it will not move in a certain preferable direction. Okay. Well, this is true only if there is no any potential difference between the endpoints of a conductor. Well, what happens if we apply a potential difference to certain points in a conductor, let's say the endpoints of a cable, a copper cable? Then in that case we produce a non-zero electric field inside the conductor. And because of this electric field, these free charges will experience a force. That's something we know from our very first chapter. And if there is an electric field in a medium, then an electron will see a force on it E times the electric field inside the electric field strength inside the medium or metal. So the next question is, what is the acceleration of the electron if we apply a certain electric field? And this is easy from Newton's second law. Just replace this force F by the charge of the electron times the strength of the electric field. And if we multiply this acceleration by the collision time, okay, the collision time is the time interval on which the electron goes freely without colliding with any other electron or atom. So during this collision time, we can calculate the drift velocity of electron from one point to another, and this will be in terms of the applied electric field, the charge of the electron, and the collision time divided by the mass. So this defines a kind of velocity, and this velocity is called the drift velocity. In that case, the electrons will move at a certain direction, in the direction of the applied electric field, and the speed of this motion will be called the drift velocity. Let's calculate this drift velocity for an example. Let's think about a copper wire which has a length of 10 meters, and we apply the potential difference to the endpoints of the wire, 10 volts. In that case, we can calculate the drift velocity. In drift velocity we have the knowledge of electric field, but we can calculate the electric field for this copper just dividing the voltage by the length of the wire, and it is just 1 volt per meter as the strength of the electric field. If you put all the constants in here, the electron charge, the mass of the electron as just order, and times the average collision time between the electrons, so you calculate this as 5 times 10 to the minus 3 meter per second. Well, it's not a very huge speed if you compare this to the average speed at room temperature, but well, this time the electron will move at a certain preferable direction. Okay, so this is just 5 millimeters per second. If you apply 10 volts to a 10 meter wire, then the free electron will move 5 millimeter per second. Okay, so let's concentrate on this wire again. And in 1 second, if the drift velocity, for example, if you apply a potential difference to this wire which has length L, and of course this wire will have a cross-section area, and we'll call this A. So the direction of the current is always from positive, from higher potential to the lower potential, from positive to negative. That means the positive charges will move in this direction, but there are no free positive charges inside the metal. The electrons will move, the free electrons will move in the opposite direction, from minus to plus, but this defines the current in the other way. So if you apply a potential difference, then the electric field inside this wire will be the potential difference V divided by the length of the wire. And in 1 second, for example, from here to here, the electron will move, from here to here, the electron will move a distance of Vd meters, because Vd is the drift velocity, and this is in meter per second. So this distance, let's call, is the distance that the electrons will move in 1 second. If you apply a potential difference, let's say V, and of course the electric field is V divided by L. So the current in 1 second we can express in terms of these quantities: the drift velocity, the cross-section area, the number of electrons in this portion of the wire, and the charge. Well, you can think the current as the flow of charges in 1 second, right? In that case, we must ask the question, what is the number of charges, or what is the number of electrons that moves in 1 second, that crosses the surface area in 1 second? So first we have to find the number of free electrons in this volume. From here to here, this defines a volume inside the wire, and the cross-section area is A, and the height of this cylinder is just Vd. If you multiply this, you will get the volume, Vd times A, and in this volume, how many electrons are there? Just the small end times this volume is the number of electrons in that region, because N is the number of free charges per unit volume. Okay, so this is the number of charges flowing in 1 second, and if you multiply this by the charge itself, then you will find the charge per unit time flowing a certain let's say point, and this defines the current. The current is defined mathematically, just the charge flowing per unit time. It's dq divided by dt, and we can express this quantity in terms of these the drift velocity, the cross-section area of the wire, and the number of free electrons per unit volume of this wire is made of, whatever the metal, and the electron charge. The unit for the current is coulomb per time, and this has a special name. It is amperes. I will write it down later. And of course you can also express this drift velocity in terms of the charge, the number of electrons per unit volume, the electron's mass, and the collision time. So in that case we get a different expression for the atomic description of the current. Well, we have a new quantity defined in here. This coefficient, the multiplication of E square, E is the charge of the electron, the number of electrons per unit volume, and the collision time. This is divided by the mass of the electron. This quantity is called the conductivity of the material. Okay, the conductivity of the material is just the electron charge square times the number of free electrons in that material, and the collision time of free electrons in that material divided by the mass of the electron. So this is the conductivity, and the larger the conductivity value we have, the larger higher current if you apply the same potential. Okay, and we have again still these terms in the current. This is the cross-section area of the current carrying wire, and this is the electric field strength inside the wire. For example, for copper at room temperature, this conductivity is very high, a large number. It is 10 to the 8. It's 100 million. And we can express now then the current, if also we replace the electric field strength by V divided by L, then the current will be equal to the conductivity times the cross-section area of the wire, the conductor, divided by the length of the conductor times the potential difference between the endpoints of the conductor. So this is the expression for the current. If you know the potential difference, the conductivity of the material, and the cross-section of the material, and the length of the material. As you see, if you enlarge the cross-section, you have a larger current with the same conductivity and the potential difference. Or if you prolong, if you use a longer cable, then this will reduce the current if you keep everything the same. We can also express the potential difference in terms of the current, the conductivity, cross-section area, and the length of the wire. If you express the potential in terms of the current, then the coefficient in front of the current, this quantity, the length of the wire divided by the conductivity times the cross-section area, defines a new quantity which we call the resistance or the resistor. So the resistance of a conductor which has length L and the material of the conductivity is sigma, conductivity of the material is sigma, and the cross-section, if the cross-section area of the conductor is A, then this defines the resistance of this conductor. Okay, so the resistance is the resistance to the flow of charges, as the name suggests, and if you make the conductor length larger, then the resistance will grow. Of course, it will be more difficult to cover a distance which is larger for a charge, and if the conductivity, of course, is large, the resistivity will be smaller because it has the material has a larger conductivity. That means the electrons will move more freely, and if you also increase the cross-section area, that will decrease the resistance, because if you increase the area, then there will be more room for the charges to move. That will reduce the resistance, and it is physically intuitive. And we call the inverse of the conductivity as the resistivity. Okay, so the higher resistivity means the less current through that conductor when everything is kept the same, and they are inversely related to each other, the conductivity and resistivity. So we can express then the resistance of a conductor as the length of the conductor times its resistivity divided by the cross-section area. And the unit for the resistance is called ohm. It's a special letter we use. The Greek letter is ohm, is the unit for the resistance. If you take the length as meters, and of course the area, the cross-section area is meter square. In SI unit system, we have as the unit of the resistivity ohm. We call this ohm. So let's think a rectangular wire, and it has a cross-section area of a square, and its size is 1 millimeter, and the length of the wire or conductor is 1 meter, and the current, of course, will be in this direction from plus to minus, and the charges will move in the opposite direction. So the question is, what is the resistance of this conductor? So if this resistance, let's say, is gold, and gold, silver, and copper, they're all good conductors, and if this conductor is made of a material which has the conductivity 10 to the 8, a copper, then it will have the resistivity 10 to the minus 8, of course. And if you use this resistance formula, L times rho times divided by A, the cross-section area, you find the resistivity of the copper as, for a 1 meter copper, as 10 to the minus 2 ohms. So it's very low resistance, right? And when you think of electrical circuits, you usually ignore the resistance of cables because cables are good conductors and the good conductors has very low resistances. But for example, glass is a very good insulator. That means its conductivity is very low, it's very small, or its resistivity is very large number. It is usually depending on the doping of the glass. It is between 10 to the 12 and 10 to the 16. In that case, for the same kind of geometry, for example, if you think this as a glass, then the resistance of this glass of 1 meter and 1 millimeter square cross-section area has a resistance of 10 to 20 ohms. Okay, it's a very large resistance because it's an insulator. Well, with for example, a 1 volt of potential difference, for example, for the copper, you will have a current of 100 amperes, and for the same geometrical shape for a glass, you will have 10 to the minus 20 amperes, which is a very low flow of charges. It's a very small current for a insulator. Well, if you, for example, have a variable potential supply, and this is called a battery, and if you can change the potential difference of this battery from 0 to 4 volt, and if you complete this into a circuit where you use a resistance and you put an ammeter to measure the flow of charges or current. Ammeter is the measuring device for the current, and we always have to use a resistor in series to measure a current, because if you connect an ammeter directly to a power supply, then this will break the ammeter, because it will produce a very high current, and in a very short amount of time when you close the circuit, this will break the electrical device, the ammeter. So you always have to use some resistors in series, serially connected to the ampere meters to measure the current. When you change, if you make a plot of the voltage, power supply of the voltage with respect to the current reading in your ammeter, when you change the voltage supply from 0 to 4 volts, you will see that the current will change from 0 to 4 divided by 50 amperes in a regular fashion, in a linear fashion. That's because between V and I there is this linear relationship. The potential difference V is equal to I times R, and this is called Ohm's law. We will see the derivation of this Ohm's law for ohmic conductors. So whenever you make this type of circuit diagram, and if you change the voltage regularly in a linear fashion, then you will see that the current will again increase in a regular linear fashion. And this kind of curves are called Ohm's law. Okay, this kind of relation between the voltage and the current is called Ohm's law. We know that the resistance of a resistor changes with temperature, and let's see now how this change happens for a specific example. And we have a silver wire which has a resistance of 6 ohms at 20 degrees Celsius, and the question is, what is the resistance at for the same wire, what is the resistance at 34 degrees Celsius? And the temperature coefficient of the silver is given as 3.8 times 10 to the minus 3 inverse Celsius degree. That means 1 degree of change in the temperature induces the resistance of this much, 3.8 times 10 to the minus 3. So let's remember what was the resistivity or resistance of a conductor at certain temperature if you know the resistance of the same conductor at a specific temperature, and if you know, of course, the temperature coefficient of the conductor. And this temperature coefficient is specific to each type of metals. As I said, as I given in the problem, for silver it is this much, and for gold it is a different number. For example, copper, it's a different. So it is unique to the type of the material. So this is the expression. How to read this expression, that we know the temperature of the conductor at T0, that's we call initial temperature, and if we want to know the temperature of the same conductor at any other temperature, then we have to multiply this the resistance with that quantity. In this quantity we have the temperature difference, and this is multiplied by the coefficient of temperature, and we had this plus 1 in the parentheses. So let's do the calculation, and we are given our 20 degrees is 6 ohms and our 34 is not known, and if you plug and chuck in everything in this expression, we can find that the resistance of this wire at 34 degrees Celsius is given by this algebra, and the final result I can calculate with my calculator as 6.252 degrees Celsius. So the temperature increases for this range of temperature for the silver from 6 ohms to 252 degrees Celsius. Well, this doesn't seem very much, and we can think of why when some conductor the temperature of some conductor increases its temperature, why the resistivity or resistance increases. Well, this can be understood in the macroscopic picture, because when we heat up a conductor, that means the average speed of electrons in that conductor will increase, because the kinetic energy increases with the temperature. In fact, the kinetic energy of a substance is nothing but its average energy per moving particle. When you heat up, the electrons will move faster, and when they move faster, their collision time also will be changed, and the collision times between the electrons will be smaller. That means this will affect the collective motion of electrons from one point to another by decreasing, in fact, this drift velocity, because the collision time now faster, and the drift velocity for a shorter time will be less. And if the drift velocity is less, then that means the current is less. And if the current is less, then that means the resistance is large. So when you heat up a certain conductor, you can figure out that because of the increased motion of charges or electrons, the resistance also will increase. We have a conductor of changing cross-section, as you see in the picture, and you are given some non-zero value of current that flows through this conductor from this end to the other, and also the value of the current is given as 10 amperes. So we call one end, the cross-section of the one end of the conductor, as A1. This is supposed to be a circular area, and the other end has another cross-section A2, which is larger than A1. This is again supposed to be a circular area, and A1 is given the radius of 1 centimeter as the radius of the circular area, and the current density on A1 is given as J1, and the current density on A2 is given as J2. So to remember what the current density is, it is just the current flowing through a cross-section area per unit area. Okay, if for example, if you are given the total current that flows through this A1 is AI 10 amperes, the question is what is the current per unit area that flows through this cross-section. For example, if you want to know the amount of current that flows through 1 millimeter square or 1 centimeter square or whatever, you multiply just the current density by this area to find the total current. And since the total current, for example, through this A1 is given as 10 amperes, then the current density that flows through A1 is nothing but this 10 amperes divided by the area of this cross-section, A1. And you can similarly find the current density that flows through A2, this cross-section. It is again just 10 amperes because the current is not changing when it flows through this conductor. The only changing is the cross-section area. Of course, if the cross-section area is changing, then the current density through this cross-section area will be changing. So, for example, for this end, the current density will be again the same current value, 10 amperes, divided by A2, the cross-section area of this end. All right. So the question is, first of all, what is J1, the current density that flows through A1? Since A1 is in the shape of a circular region, then we have to divide the total current that flows through A1 divided by A1. Okay, and the second part of the question is what is what is the radius of A2 if you are given that the current density that flows through A2 is only 1/4 of the current density that flows through A1. Okay, so remember we called J1 as the current density that flows through A1, and you are given that J2, the current that flows through A2, is just J1 divided by 4. And if this is the case, what is the radius of this circular area of this end of the conductor? So, as I said, when if you want to find J1, like what you do is just divide 10 amperes of total current through the cross-section area, and the cross-section area, since it's a circular region, it's pi r square, and pi times 1 centimeter square. If you, of course, have to convert to meter if you are working in the SI unit system, then that will mean J1 is equal to 3.18 times 10 to the 4 amperes per meter square. Of course, this should be squared. Sorry about the mistake. Let's put square in here. But if you want to find the current density in terms of amperes per centimeter square, then you just leave without conversion to meters as 1 centimeter, right? 1 centimeter square. So you will have, in that case, the current density 3.18 amperes per centimeter square. Okay, so this is J1, and in the second part, you are asked to find J2. Sorry, you are asked to find R2, which is the radius of the second cross-section area, A2. And you are given this relation between the current and J2, and it is 10 divided by pi R2 squared, but you are given that this current density is just 1/4 of the current density at A1. So if you equate this value to only 1/4 of 3.18 amperes per centimeter square, you will get an expression relating the radius of the second circular region, or radius of the second cross-section area, and you can easily solve for R2 by using this equality. It's just simple, and if you of course, do the calculation, you will find R2 as 2 centimeters. So as you see, since the area is proportional to the square of the radius, then if you have only 1/4 of the current density, then that means you will reduce the radius to, or you will increase the radius to twice, because when you enlarge the cross-section area, you decrease the current density, because for the same current that flows through a larger area, that means your current density will be less. Right. We have a conductor in the shape of a trapezoid, and we want to calculate the resistance from face A to face B. So we're going to calculate the resistance in this direction, and if you go along in this direction, the cross section is a rectangular of size W and Y. But the thing is, when you go from face A to face B, the height of this rectangle, which is Y, is increasing from Y1 to Y2. So it's a changing cross-section area. And from side waves, that means we have a trapezoid in this shape, okay, and we are going from this side to this to calculate the resistance, and the total length of the conductor is L, and the initial height is Y1, the final height is Y2, and this height is increasing linearly. Okay, so we can think this conductor as the sum of infinitesimally thin rectangular resistors. Okay, so you can think if you fix this horizontal axis as X and just pick up a rectangular slice of this rectangle of this conductor of thickness dx, and you can think the resistor as the addition of these rectangles of changing cross sections from this side to the end. So of course the total resistance will be sum of the resistances of these slice of rectangles, and if we can express the resistance of one of these thin rectangles, then we can take the integral to find the total resistance from this side to this side. Okay, so when you think a rectangular shape of conductor which has thickness dx, and when you try to write down the resistance of this slice of rectangle from this side to this side, the length will be dx. So the general expression for the resistance is the length of the resistance divided by its cross-section area and times the resistivity of the material. And the resistivity of the material is constant for the uniform for a unique material. Alright, so our aim now, again, to write down the resistance of this slice of rectangle, the conductor, and we call this resistance as dr, and the height of any of these slides will be written as y, and of course the width is not changing when you go from face A to face B. The only thing is we have to express this height as a function of x from this side to the other, because the length of the conductor that we are thinking of these slices is dx, and we should be able to write down this height in terms of x, because in the integral the variable is x, and we should be able to write down every variable in terms of x. And you look at this height, you can easily write down that, you can easily see that this line is just a straight line which has slope as y2 minus y1 divided by L, and its initial position is y1. So it is very easy to express this y in terms of x, and the height, initial height of the our trapezoid conductor, and the final height, and also the total length. We can easily write down this y in terms of these parameters. So the rest is to express the resistance of this slice of rectangles, and it is just the resistivity of the material rho times, since the length will be this thickness in our case, divided by the cross-section area. The cross-section area for rectangle, of course, it's w times the width times the height, which is y. Okay, so but y is already expressed in terms of x, so we can replace y, this quantity, y2 minus y1 divided by Lx and plus y1. So everything is expressed now in terms of some constants and x. And the next is to be able to write down the total resistance, we have to take this integral of dRs. And of course, since the integration variable is x, the integral should run. You can fix this face as x is equal to 0, and this is, in that case, will be the total length of the conductor, which is L. So the integration limits will be from 0 to L. And we have everything inside the integral as a function of x. And of course, I should erase this extra w in here. We don't have a w in here. Okay. Now we are ready to take this integral, and it's very easy to take this integral because it's just a logarithm, natural logarithm. And when you put everything, the limits, and evaluate the endpoints, then you will get this expression for the resistance of a conductor which is in the shape of a trapezoid. We have a hollow cylinder, it's a conductor, and we want to calculate the resistance of this conductor if you apply the potential difference between the inner surface and the outer surface. So when you apply a potential difference, of course, the current will flow in the direction of the maximum change of potential. So when you apply this potential difference, the current will flow from the inner surface, okay, toward the outer surface in the radial direction. So that means we have a radial current, and when this current flows, the current will flow through a cross-section area which is in the shape of a cylinder, and this cross-section area is just the side area of a cylinder. Okay, and of course the cross-section will change because when you go from inner surface to the outer, the radius will change. That means the circumference of the cylinder that the current will flow is changed, and then this will change the cross-section area. So we have a change in cross-section area. In that case, of course, it's not very simple to write down the resistance just in the general formula rho times L divided by the cross-section area. But the total length of the the height of the hollow cylinder is L given. But the thing is, you just be careful, the current is not flowing from this side to the other end of the cylinder in this direction. Okay, it's not the case, but the thing is, the current is flowing through from the inner surface toward the outer surface in this radial direction. Let's picture this in this better picture, the cross section. So we have the inner radius of this hollow cylinder as A, and the outer radius is B, so the thickness of the conductor is B minus A. Okay, so that means the length of the conductor that the current flows is B minus A. But of course, the cross-section area is changing. So one way to think, to calculate this resistance is again to imagine this hollow cylinder as the sum of cylinders which has thicknesses dr running from r is equal to A to r is equal to B. So when you think this, for example, the darker region, this is a cylindrical shell which has the thickness dr, and if you think that the current is flowing from the inner surface of this shell toward the outer surface, then in that case the length of the conductor, the shell, will be dr. Okay, and what about the cross section? The cross section will be the circumference of this cylinder, okay, times the height of the cylinder, which is L, and L is fixed for all of these cylindrical shells which are running from the inner surface to the outer surface. And if we can express the resistance of these shells, then the total resistance of this hollow cylinder will be just the sum of all these resistances of the cylindrical shells. And one of these, we will call the resistance of these shells as dr, and when you take the integral of these resistances, then you will find the total resistance of this hollow cylinder from the inner surface to the outer surface. So when we apply the potential difference from between the inner surface and the outer surface, since the surface will have the constant, will have all over the surface, we will have the constant potential, and then in that case the current will flow in the radial direction, in the direction of these arrows. Okay, so the resistivity of the material is fixed and it is rho. So the general expression for the resistance is just L divided by A. L is the radial thickness in that case, and of course the since the cross section is changing, then we express, as I said previously, the resistance of this one of these infinitesimally small thickness cylindrical shells as dr. So it will be the length of the conductor in that case for this shell is dr. So we put dr in here, and the surface area will be just the circumference of this ring 2 pi r times the height of the cylinder L. So this is the side surface area of a cylinder. Then we already expressed every thing in this expression dr in terms of one variable r. Okay, and this r is the radius of these cylindrical shells. So I think we are ready now to take the integral of these infinitesimal resistances to find the finite resistance of this hollow cylinder, and just take the integral. But what about the limits of the integration? Since the inner surface is at r is equal to A and the outer surface is at r is equal to B, then the limits of the integration will be from A to B, and everything else apart from dr divided by r is constant. You can take the all these terms, rho, L, and 2 pi outside the integral, and the result is simple because the R over R integral is just the natural logarithm. I mean, if we put the limits of the integration, then you will get this final expression for the total resistance of this cylindrical hollow from the inner surface to the outer surface. Well, if you ask another question concerning the same hollow cylinder, if you apply the potential difference between this surface and the this surface, which is in the direction of the symmetry axis of the cylinder, then it is very easy because the cross-section area never changes, and the cross-section area is just the area of this annulus, and it's just pi b square minus a square, pi times b square minus a square. This will be replaced by a, and the total length, because the current in that case flowing from this side to the other side in the direction of height, or L, the total length will be replaced by this capital L, and rho times capital L divided by pi times, in parentheses, b square minus a square will be the resistance if the current flows in this direction. Of course, this is another problem, and the problem changes when you think the current flows from the inner surface to the outer surface. Okay, we have a material which is in the shape of a quarter annular disc, and we see the dimensions of this material. Geometrically is the 1/4 of a annular conductor or a material, which has this inner radius from the center to the face B as small b, and from the center to face A it has the radius small a. And we are interested in to find the resistance between the face D and face E. So the current flows in this direction or the other way, and we want to find the resistance in terms of the dimensions of this material. When you look at carefully, we can think this quarter annular disc as the slices of quarter rings, which is in this shape, which are parallelly added from face B to face A. Let's picture these quarter rings. So the thickness of the slab in this direction is T, is given, and it's the same on everywhere, every point on the material. So the thickness is T for this quarter ring, but the lateral dimension of this, the cross section, the lateral dimension of the cross section of this ring is we call as dr, because these rings are changing from the center to the outer face in the radial direction. So that's why we call these lateral dimension as dr, infinitesimally small thickness in the lateral dimension. So we can think this disc, quarter disc, as the parallelly added quarter rings of this shape. Of course, the radius of these rings are changing from B to A. When you add them parallelly, the radii will change from B to A. So this is the shape, and we add these rings of different radii in the parallel direction, in the radial direction. We add them parallelly. So we are interested in finding the resistance from this side to that side. So you can think of these rings as parallelly connected resistances. Then to find the equivalent resistance, we will use the expression for the parallel addition of resistances. So you can think these as resistors of different lengths. Of course, since they have all different radii, they will have different lengths. From this side, let's say from D to E, they are connected parallelly. So the equivalent resistance, of course, for this will be the inverse of the equivalent resistance will be equal to the sum of all inverse resistances of these conductors or materials. Well, the question is, how can we then proceed to find this inverse resistance? So the inverse resistance is, since the inverse resistance is the sum of these parallelly connected resistances, but these resistances are added continuously. That means we don't have the finite discrete resistors of the different size L's, but they are in fact changing continuously. So this sum will be, as you can guess, will be in the form of integrals. So what we calculate, in fact, we will express one of these inverse resistance of quarter rings as infinitesimal inverse resistance, and then we will take the integral from r is equal to b to a. If we can express the resistance of each of these quarter rings as the variable r, which is the radius of this quarter ring, then we will be able to take the integral. So let's concentrate now on this infinitesimal inverse resistance, d1 over r, and of course the equivalent infinitesimal inverse resistance will be the sum of these infinitesimal inverse resistances, and this will be integral because they are changing continuously. So let's express with these parameters given for this slice of quarter ring, it express the real resistance. Then the general expression for the resistance is just the resistivity of the material rho times the length of the resistor from this side to this divided by the cross-section area. So the length, if you take this r as the radius of the quarter ring, then this length from this side to that will be 2 pi r divided by 4. It's the quarter of a circumference of a ring of radius r, and the cross-section area is simply, since it's a rectangular region and the cross-section does not change along this direction, it will be t times dr. Well, it seems that the cross-section area is changing because we are using dr, but dr is not changing when you go along this direction, okay? But the thing is, we will take the inverse of this anyway, because we cannot take in the integral of this kind of expression where the integration variable dr is in the denominator of a expression. So, but anyway, we need the inverse of inverse resistance, so we are okay to express this inverse resistance. Just take the inverse of this expression, 1 over rho times 2 divided by pi times r, and the thickness t times dr. So the rest, in fact, is easy since we are already expressed this inverse infinitesimal resistance, infinitesimal inverse resistance. Then the rest is to find the total inverse or equivalent inverse resistance as the integration of this inverse, the infinitesimal resistances. Well, what about the, of course, the limits of the integration? The limits of the integration, since the variable is r, and r is the radius of these slice of quarter rings, so it will change from r is equal to b to r is equal to a. So taking this integral is very easy, and the result is just 2 times the thickness of the slab material divided by pi rho times the natural logarithm a divided by b. But this is the inverse of the equivalent resistance, so the real resistance to find the real resistance, just take the inverse of this quantity, and it is nothing but the resistivity of the material rho times pi divided by 2t natural logarithm A divided B. Let's check. Okay, let's check this when A is equal to almost B. That means we are thinking of very infinitesimally thin, in the lateral direction, infinitesimally thin resistance of a radial the quarter ring. So to do this, of course, we will take a very small to B, where A is larger than B, but if you think that they are very close to each other, then we should be able to express this ratio A divided by B as 1 plus A minus B divided by B. Well, you can check this. So the idea of doing writing this ratio like this is to be able to express the natural logarithm ln A divided by B in terms of only A and B, so that we can get an expression for the resistance only in terms of A, B, and thickness and the rho. So the natural logarithm A divided by B when A is very close to B is A minus B divided by B, and we to get this result we have used the approximation formula for the natural logarithm when we have the natural logarithm of an expression in parentheses 1 plus x, where x is very small number, and this applies to our case because A is very close to B, and this is nothing but x. So we can replace the natural logarithm A divided by B by A minus B divided by B. So we can express the resistance of this one of these quarter rings. Then we have this expression rho 2 pi B divided by 4, which is the 1/4 of the circumference of this ring of radius r. Okay, this is L. And T times A minus B, well, A minus B is just this side, okay, and T is the thickness, so this is just nothing but the cross-section area of this ring. So we verify that in fact this result is correct, and by doing this approximation we just recovered the resistance of this infinitesimally thin quarter ring.